Friday Eve. I hope you're enjoying your day, and I have a nice panel for you guys. We're going to talk a little bit about quantum, and quantum hardware specifically. So the title of the talk is Race to Scale, which quantum tech will lead and why. Everybody's interested in quantum these days, so we're going to touch a little bit about it. All right. So this is the International Year of Quantum, and that's a little blurred there. How do you turn this down? I'm not sure if I know how to turn it down. Is it you guys? Are you guys off? Is it me? No, yeah, see if you can turn it down a little bit. I want to start a little bit with the audience survey. As you guys came in, there was some questions. So this is the first one. We've kind of done some real-time data analysis. And so who do you mostly identify with? 70% are students here. We have a little bit of academia, a little bit of industry, and a little bit of government. Interesting. Not much on the private equity or finance side. What is your education level? Lots of masters, a few doctorates, and a few undergraduates. Thank you, Marcia. It's still a little bit. What is your familiarity with quantum mechanics? So most people say some, and a few people say lots, which is probably our academic crowd. What interests you about this event? So there's some curious people, there's some career aspirations, there's looking for collaborators, and some people are interested in APS. So APS is a good organization to join if you want to do quantum stuff. All right, let's talk a little bit about our panel. This is our panel. They're seated up here. I don't think I have the next slides in order based on the way you guys sat. I kind of have them in the order in which you guys gave them to me. So let's start with Paul talking about Alice and Bob, and I will silence this thing.
Check. Okay. Hi, everybody. I'm Paul Cassabaum. I'm the head of public sector at Alice & Bob. We're a French-based company that does quantum processing, unit design, GPU design. If you've heard of the different modalities of qubits, we are a superconducting modality, and we design, you may have heard of transmons. We don't do that. We do what are called Schrödinger cat qubits. And if you go to the next slide, the thing that drew me to the company technologically was that the physical design of our so-called Schrödinger cat qubits is such that the physics of the way that the qubits operate suppress one of the two main sources of noise in quantum computers. The two main sources are so-called bit flips and phase flips. And these qubits, the physical design of them, suppress bit flips completely, leaving only phase flips for quantum error correction. So our quantum error correction is just a one-dimensional problem instead of a two-dimensional problem like it is for everybody else. So we can have about 100 times fewer physical, tangible qubits to support fault-tolerant so-called logical qubits. In particular, for our designs, you only need 15 physical, tangible qubits to support a single logical qubit. Other designs, especially in the superconducting modality from other companies, that number is, instead of 15, is closer to 1,000 or 1,200. And there's savings and ramifications all through the technology, from its footprint, how big are the chips, or in other words, how many logical qubits can you stuff into a single dilution refrigerator. We think we can fit orders of thousands of logical fault-tolerant qubits in a single chip in the future. It also impacts things about how much energy does it take to run your quantum computer. For us, it's 2 orders of magnitude fewer. But just to keep it brief, I'll stop there. Thank you.
Next, we have T. He likes to go by T, from ORCA Computing. Go ahead.
Hello? Hello? I don't think it's working. Hello? Oh, is it? Okay, great. Well, thanks everyone for having me here today. Thanks to Horatio and APS for putting on this great discussion and this great event. My name is Tianan. I go by T for short. I'm the CTO at ORCA Computing. My background is more in integrated photonics, a little bit of quantum technologies. At ORCA Computing, I lead the transition of our breakthrough technologies and fundamental research in our labs into practical systems that we deploy. ORCA Computing is a full-stack photonic quantum computing company. We have a deep expertise in quantum optics, integrated photonics, and atomic physics. We're headquartered in London, but as of last year, we have an office here in Austin, Texas, and we're really excited to expand our presence in America over the next several years. What differentiates ORCA from many of our competitors is our commitment to delivering products to customers. So as of now, we have more than 10 systems that have been delivered and installed at customer sites around the world. And this underscores our philosophy of getting quantum technologies into our customers' hands early and often, learning from, engaging with, and collaborating with our customers so that we can continue to evolve and improve our products over time to maximize their business value. So in the market right now, we have our PT2 photonic quantum computer, which has already demonstrated unprecedented performance across multiple generative AI and optimization tasks. So I'm looking forward to the discussion today and sharing ORCA's perspective on the future of quantum.
Thank you. Next, from Vescent Technologies. I guess it's just Vescent, right? Eduardo.
I'm Eduardo Teza from Vescent, as we call ourselves, formerly Vescent Technologies. We live in a little different space than the other panelists here. Vescent does not actually make quantum computers or quantum sensors or other quantum devices. We're kind of like a chip maker, so to speak. Right, so we supply components, building blocks to people who are specifically trying to build quantum computers and sensors and quantum networking devices to companies who manipulate atoms, at atomic level systems. And so you can see in my little diagram here, we're really kind of a tier 1 supplier to atomic computing companies, atomic clock companies, networking companies, and sensing companies all. So we actually don't do the application like these guys do, but we actually build the hardware that you can then piece together. So in fact, next slide please, and show you one very specific kind of product that we manufacture. It is called an optical frequency comb. It won a Nobel Prize was awarded to Ted Hedge out of Max Planck Institute and Jan Hall out of NIST in Boulder, Colorado. And that's our lineage out of Jan Hall's group, that actually can tie together RF, the radio frequency domain, to the optical domain, and you can use it as a tool to control your atoms. So on the left side, for example, I'm showing you that you're using an optical frequency comb to manipulate strontium ions for, say, a quantum computer, and on the right side, or at least what I'm looking at, on the right side, for manipulating rubidium, for using it for what's called a Rydberg RF sensor. These are both quantum devices, and so people who use atoms and manipulate them would use a device like ours to properly prepare the atom to do the sensing or computing.
Thank you. Greg, why don't you tell us a little bit about Qblox?
Absolutely. So my name is Greg Carmen. I'm the general manager for North America for Qblox. We're manufacturing control electronics where we bridge quantum and classical systems, turnkey computing systems. We're a Netherlands-based company. We have over 150 deployments, clients, installations of our control stacks around the world. We just recently opened our North American operations. That was in January, and we are making a significant long-term human capital, financial capital commitment to North America. So you can think of control stacks as the nervous system for a quantum computer. So what we do is we control the qubit, our control electronics do, and we measure the readout from the system. So if you think about the technology stack, you got to have a QPU. You usually need to have a dill fridge to keep it, extremely cold, so you can have a stable environment for the qubit. And then you have your control electronics, and then you have cabling, and then you have software to do everything from calibration to compilation to quantum error correction to actually, performing applications in the future. If you go to the next slide. So I think it's a build slide, potentially. But we have over 150 people, mostly PhDs and scientists with some sort of quantum information science background. And many of those are applying those skills into engineering roles as we're designing and manufacturing the next generation of technology. Currently, all the control electronics, including ours, are built on FPGA technology. Over the course of the future, as this starts to evolve, you'll see it, the entire industry, including us, moving to an ASIC-based architecture and manufacturing process. But there's still a lot of work to be done with that. So we have a lot of plans to grow across North America. We've got some key centers of excellence already in North America, one at MIT, one at the University of Sherbrooke in Quebec. But it's growing. We're going west, young man, so to speak, as we continue to add more centers of excellence. And then we partner with pretty much everybody in the industry. So as control electronics, you got to be able to work with all the different GPU manufacturers. You got to be able to work with all dill fridges. You need to be able to work with all cabling systems. You need to be able to work with all full stack systems like Alice and Bob. You need to be able to work with the networking systems like ORCA. You need to be able to work with all the software above it. So we like to think that we're a pick and shovel, if you've ever heard of that metaphor in the industry, but it's a nice place to be in a very fast-growing industry. That's a little bit about us. I'm looking forward to the conversation. And clearly, I was the last to deliver the slides because I showed up last in the slide deck. So my apologies for us.
No worries, no worries. We're all here having fun.
That's right.
All right, so we'll take a little step back because quantum technology has already been part of our lives. So what are we talking about here? It's sort of like talking about AI, right? There's several different kinds. But, if you've ever had an MRI scan, you have used a quantum sensor. If you've ever had a compute, well, you've used quantum mechanics in band gap theory into how transistors work. So to some extent, our world is full of quantum devices already, but that's not really what we're talking about here. So what are we talking about? So the key things that are being leveraged now for some of these newer technologies have to do with superposition and entanglement. And for anyone who's not real familiar with these concepts, superposition is sort of the idea that, and these are videos, so if you focus on the left side, you can see the shadow of a surfer, and the surfer's in two spots at the same time, but it's a single surfer. And as soon as an observer shows up, it becomes one surfer and it has a state. This is courtesy of NIST. So the other concept has to do with when you have more than one qubit or more than one interacting state, and that's where we show the concept of entanglement. And one way to think of it is these two qubits have been interacted together to where they are now correlated with each other, and they're now behaving in a very correlated fashion. And then those correlated qubits act as one. And it doesn't matter how far apart they are. When you measure one, you know what happens to the other one because they're one thing. So if you measure one part of one thing, then you know the whole system. And so as this video shows, you can see that they're kind of in a superposition, and then as soon as the ruler represents the measurement, as soon as the measurement's made, it snaps to a state. That's the concept of entanglement, where you can make multiple qubits act like one system. So these are properties that have been known for a while, but it's just now starting to kind of hit the, well, I wouldn't say just now. It's actually been getting de-risked for a very long time, but it's just now kind of reaching the edge of commercialization. There's some sensor applications that are already in existence. To give you, we've talked about modalities, so you know, when you think about CMOS, it's not really a modality, it's all just transistors, right? Wide bandgap might be another modality of transistors, but not in the same way that in the quantum world. And I know this is an eye chart, but on the left is qubit modalities by companies, and on the right is qubit modalities by research groups. And there are superconducting, photonic, ionic, neutral atom, and I already mentioned topological, I can't read all of these. And then in the outer circle are all the names of all the companies. And yes, I did see you guys in there. So this is a pretty comprehensive assessment of who's doing what. That was put together by Michael Crick. I think he's French, so it might be Mikhail Kurik. I'm not sure how he pronounces his name, but he gave us permission to use this. Each of these modalities are very different. You can have many quantum systems, and for example, I have seen papers where the vibration of a microelectromechanical device has been entangled with a photonic channel. And so they were able to use this microelectromechanical device to modulate a laser beam going through a waveguide. And so entanglement can be across modalities if you design it right. And so this is like really kind of complicated technology because you're not just talking about a transistor, you're talking about atoms can be mixed, ions, you're talking about photons, you're talking about quantum interference, you know, squid devices, superconducting quantum interference devices, and these can all be manipulated in quantum ways and made to work in unusual ways. And the top three applications of this kind of quantum technology is, of course, the quantum computing that people know about, and a secure form of communication with quantum key encryption and quantum key distribution. And so it's going to be the replacement for standard RSA encryption or even the post-quantum encryption that is coming out of NIST. So there are already networks installed that are using this kind of quantum behavior in order to communicate in a way that is not possible to eavesdrop on. All right, so that's as much as we're going to cover, but the idea was to get everybody kind of up to speed on both, you know, what we're talking about with quantum and the breadth of the topic. All right, so let's go ahead and start the panel. There's going to be basically two questions that I ask, and then we're going to go to audience questions. So the first question for you guys, in the quantum consolidation that is coming, which modality do you think will dominate in each of the three markets, the computing, networking, and sensing, and why do you think that? Who wants to go first? Go for it, Greg.
So I'll take it from a computing perspective. I think that picking just one winner at one point in time is probably not the way to look at the market. I think there'll be, over time, you'll see certain modalities winning. And let's just say superconducting right now. It's growing in terms of the amount of research that's being done, the amount of logical qubits that we're able to generate. But will it be the long-term winner? It's indeterminate. But I do think there'll be more than one winner over time. I don't think that every modality serves all purposes for complex computational requirements that you can put quantum computing on. And I don't think that just because you're a winner in the beginning means you'll be a winner in the long term. And in the long term, I don't think there'll just be one winner. I think that's probably just trivializing the complexity of some of the problems we can solve and trying to just make it homogeneous with, well, it's only going to be one modality that can solve all those complex problems, that each one of them are highly different from the other. So my point of view is there'll be more than one winner. My point of view is there will just be one winner one time. And I think it'll be continuing to evolve over 3, 4, 5 decades.
So do I understand you correctly? Are you insinuating that certain quantum algorithms might work better on certain modalities than others?
I'm not the expert in that part, but it appears that there's evidence that might be the case.
Interesting. Paul?
Yeah, I think in broad strokes I agree with you, Greg. And the reason you can have multiple winners is because there are probably going to be multiple markets, even within computing, within sensing. So you may, for example, in computing, I can imagine at least 2 markets where you have a quantum computer with the footprint of a football field, like a psi-quantum. That limits you to a market of customers with really, really deep pockets, maybe the Department of Defense type of customer. Then you have quantum computers that can fit, the footprint of one of your chairs, right? That has a significantly different price point, and then you can have customers still large initially, but not as large as the Department of Defense. And you have these different use cases. I don't know if the modalities are really going to vary the performance of the algorithm, but you can talk about how many logical qubits are in that system. That's the footprint size versus the smaller chair footprint size. And if you have on the order of 100 logical qubits, you can do really simple material science problems. 1,000 logical qubits, you can maybe start doing simple chemistry problems. And then you need to go to hundreds of thousands to talk about cryptographic problems. So a government might care a lot about breaking cryptographic codes and go for that 100,000 plus logical qubit goal line as quickly as possible. Maybe a big football field sized computer is better for that sort of initial value. Whereas if you're considering material science or chemistry, you might aim for the smaller system and think of that as your initial one.
Go ahead.
So definitely agree with points that you both made. One thing that I want to, clarify for the room so that we're all on the same page is that there's nothing magical about quantum computing and the algorithms that you're able to run on a quantum computer. Fundamentally, the classes of problems that you're able to run on a classical computer, you're able to run on a quantum computer, vice versa, at least for a universal architecture. So in terms of a universal architecture, in my mind, the modality that would win, or the technology that would win, is one that does one simple thing really well, which is scale, right? So as an industry, we've proven that quantum is real, we've proven that it works, but we haven't proven that we're able to scale that technology to the point where it provides true utility to customers and provides and solves the business cases that you mentioned, right? So in terms of a universal architecture, whether there's one winner or whether there's multiple winners, I think that's still up to you. One thing that we've been discovering at ORCA, though, is that in addition to the universal architectures which can solve all the classes of problems, there's application-specific architectures that are interesting as well. And that's what we're addressing with our near-term systems that we're deploying to the market today, which is all on our roadmap to deploy the universal architecture. lot of different applications of quantum computers and a lot of different ways to bring the different technologies together to solve very specific problems in different industries. Also, I just want to say that I'm very biased. And so in terms of quantum computing in particular, photonics will definitely
So let me ask you one follow-on question. You're expressing that there are niche markets. Is that sort of like a hard-coded version of a quantum computer as opposed to general compute? So it's like a ROM. It's the equivalent of having a ROM processor or an FPGA. It's not like an FPGA where you program.
Yeah, it's like a hardware ASIC, essentially.
Right.
Yeah.
Okay.
And I think that in the realm of quantum, in terms of the classes of quantum that we're looking to solve, this type of hardware differentiation is even more pertinent because we're really diving into the really deep niches of what we're looking to solve as a society. Right? There are specific species of atoms, for example, that are very useful for sensing very specific things, and so hardware that can interface well with that species of atoms would be preferential to compute that information, as opposed to a universal machine that potentially could take up the size of a football.
Yeah, and to your point of like a hardware type of ASIC, quantum computing hardware is designed specifically for some particular use case. If you all heard about Google's initial quantum supremacy paper and IBM's more recent utility achievement paper, those architectures were designed for particular problems.
So most everyone is hard coding today, as opposed to programming. Okay, interesting. I did not know that actually.
And I would just add to that when we talk about the various use cases and how we aren't solving a pertinent utility yet, in addition to the material science challenges and the physical challenges of just creating those logical qubits, it's about shrinking the size, it's about density, bringing everything to a smaller footprint. It's about bringing the overall cost of making getting the supply chain and bringing it all down in such a way that it's a reasonable investment, even if it's the size of a football field. It's not $1 billion, it might be something less than $1 billion, like 999 million or something. But bringing the size, the energy consumption, the heat radiance, and the cost per qubit down. So it's scalability on multiple factors until it becomes useful.
I really appreciated when you set up the introduction and you couldn't even read the print. There's so many different ways to do it, right? And so what does that tell you? It's early days. We're still figuring out, and this was a really good point, is like, we can show that it's possible to do quantum computations. Now, if you have a few dozen qubits or maybe a few hundred qubits, that's great, but you can't do that much with them, and that's why you have to go, and you're not programming. But the real point is, can you scale up that you have millions of qubits? No one's really broken through that barrier, and that's why there's so many different approaches right now. Everyone's testing the waters. What are the fundamental engineering limitations on how do you trap millions of atoms and direct laser beams on them and keep them all within a reasonable size and cost? And
move them around so that they can interact.
How do you build a laser that's actually going to manipulate all these millions of atoms? And so this is all, you kind of step back and go, am I even at the UNIVAC stage of quantum computing, right? So, right? Yeah, we're just starting out, but there's a lot of potential. It's clearly doable, but which way is going to win? For me, it's far too early to tell. Like I said, we supply hardware to companies who do atomic-based computing and sensing, and they all have different ideas.
I wonder how many people know what the UNIVAC's reference is. Careful with your use of old jargon.
Okay.
I prefer to think that we're in like the mid-1970s in the personal computing market, where there's apple made out of plywood with a bunch of transistors in the middle. I think that's
That's
probably
bringing it
closer to
forward
real.
20 years.
But I'm thinking there's like
Still, it's-
but there was like a 40-year timeline to get to the real personal computer, which we all have in our pocket right now. But it started with plywood and transistors, and so that's the analog I get with it. But UNIVAC is a good one too.
All right, so let's take this. I mean, I think we talked mostly about the quantum computing side of things. What about networking? What about sensing? I mean, from what I'm reading, the sensing applications are going to be the first to market, right?
I would say in the sequence of kind of like what's marketable, I actually, in my slide, I actually broke it out into 4 segments. So we look at computing, networking, sensing, and timing.
Oh, true.
So timing, so these days, time is very important to us because every single transaction we do is based on time. You have in your pockets phones that are tied to the GPS system, which is basically a network of clocks in space. So you get nanosecond timing in your pocket for free.
No, we have to pay for it.
And but actually, timing is very interesting these days because, in fact, just when was it? Just last week? What was it? Someone from the EU was flying to where? Yeah, in the GPS jam. So GPS is regularly being jammed now, and over Ukraine airspace. Every once in a while, there's a story in the paper who somebody decides to take off and have a long lunch and has a GPS jammer and gets too close to the airport. So, look, GPS is fundamentally a very powerful technology, but also a very at-risk technology. So it can be jammed, it can be spoofed. And so right now, the immediate push by defense complexes and all the major Western powers is how do we back up GPS? And that means building atomic-based clocks, high precision clocks, and these are quantum devices. They are quantum devices that you can bring around with you. And so I would say that's actually an immediate need right now. And our Department of Defense is in fact pouring a lot of money into this technology. I would say then networking being second, or sensing being second, networking third, and computing is like that's the harder one, but the most exciting one.
Yeah, and actually the DIU, which I saw has a presence here, their first quantum tech portfolio project, when they opened this 6th new portfolio, Quantum Focus, the first application was for navigation, motivated by GPS jam.
And those of you who are like people from UT Austin, apparently, I was told that if you try and ride one of the electric scooters or whatever on campus, that it'll slow down when you get to campus because they're spoofing to slow everybody down on campus. So you've experienced GPS spoofing because the University of Texas is doing it.
So if you're spoofed that GPS signal, you go faster.
You may not go farther, but so sensing. One of the things I find interesting about these quantum technologies and sensing is just how powerful it is at just running the noise floor way down on a lot of measurements. The sensitivities associated with the sensing applications are really pretty impressive. Do you see particular modalities dominating the sensing world, and why?
At least from my perspective, we work with a lot of companies who do what are called Rydberg atom sensors. And so you take an atom, a neutral atom, and you excite an outer electron to a very high state, so essentially near ionization but not quite ionized. And that means it's very sensitive to interacting with radio waves. and so it becomes a very broadband receiver. So you think an antenna might have a specific range it's operating on. An atom is basically a very broadband receiver, and it becomes a very powerful, very compact device. And so that's kind of the technology that I think is kind of in the lead in terms of sensing, but it depends on what we're sensing. So you can say the word sensing, so that's electromagnetic waves. Well, what if you're sensing gravitational fields? What if you're sensing magnetic fields? And so there's different modalities like sensing magnetic fields. There's a technology called NV diamond, neutral vacancy diamond, where you can put in defects, and that becomes a magnetic sensor where you use laser beams to repair those defects to become sensors. And so again, we're talking about, well, it depends on the application. So there's no one technology just kind of wiping out the field, winning everything. What you want to do is that then you kind of pick and choose what quantum approach you want to use to get there.
Yeah, and the use cases for quantum sensors, like the technological challenges are very different than for quantum computing. Because in sensing, sometimes many applications will have size, weight, and power restrictions. So if you have a giant Bose-Einstein condensate-based gravimeter, you're not going to fit that on a drone. Right? So if you want a quantum sensor for navigation on your drone, you need to bring that size and weight down. You're probably going to flip over to a totally different modality. So I think there are going to be lots of different sensing markets where the use case, these size, weight, and power constraints really drive the decision for your modality. Just because NV diamonds are great for drones and aircraft doesn't mean they're the best for every use case.
All right, I have so some of these modalities have to be fabricated with immense precision. Others, you get the qubits all the same by using an atom or an ion. What about the manufacturability of these different modalities?
Yeah, that's a really good point, and I think that's what people are exploring now. It's like, as we were talking about the scalability, that's hand in hand with the manufacturability. It's like, that's all technology that needs to be developed. Right now, a lot of these devices that are being built, they're ideas that were spun out from laboratories across universities and national labs all around the country. And so, right, these are being built for the first time, second time, maybe. So companies have built a few of them. We're just getting to the point where people are starting to investors are actually putting down money and say, build a plan to mass produce this. We're just getting there. And so, and some of the big ion computing companies have just recently done that. And so that's a big problem. That's just, I won't be just engineering, but it's a lot of engineering, right? And so people have to kind of sit down, well, how do I make this manufacturable? Is it scalable? And that's, and if I'm going to scale it, SWAP, size, weight, and power, in what's called SWAP-C, size, weight, power, and cost, are all part of the equation. What's a viable business model? So now all that's starting to pile in on top of just, hey, there's all these physics choices we get to make in terms of the modality, but now we got to start thinking about it as a business, and so that's layered on now. So again, that's why I kind of keep saying it's early days. We've got a lot of things to figure out. There's lots of other pieces, and so there's a ton of work yet to be done in terms of scaling this up to being manufacturable in volume and making it cost effective.
Yeah, just to speak from my experience at Allison Bob, we're building things at a very small volume to quickly iterate on our designs. And we have so far relied on academic partners who have nanofabrication facilities on campus to design our chips. We're just starting to move the fabrication to within our company's boundaries and staff. Still, we expect another transition in the near future to work with commercial partners running foundries to scale up to larger volumes. So we can be the designer, not the at-scale manufacturer ourselves. And in my conversations with different foundries in the U.S., what we're asking them to do is beyond their capability currently. They need to do fundamental R&D to go from the sorts of chips that they're used to fabricating to the types of chips we need. And so I'm expecting this R&D to really be coming out of universities. So the recent investment in at UT Austin for the Texas Institute for Electronics. I got to visit their campus today and I saw them unboxing new nanofabrication machines to start making use of the combined $1.5 billion of investment in nanofabrication. I think we're going to see, we're going to need fundamental basic research in how to produce the sorts of technologies that we need for Quantum 2.0 at scale, to go beyond the teeny tiny prototyping volumes that companies are operating on right now.
And I'd add to that when you saw the diagrams before with all the companies working on all the modalities and all the research labs, if you were to overlay those geographically, you're going to find some concentrated hubs around the world where the work is being done. And if you were to take another element, which is the states and the regions and the countries, and overlap that with those same circles, you would find that certain states, certain countries are providing a lot of incentives to make sure that the research is occurring in their area. That means jobs, that means federal dollars, that means state dollars, so that the manufacturing that eventually comes out of that stays in the region, which means jobs to build foundries, jobs for people actually working in them. And it's a big project and it's highly decentralized. And it very rarely happens like this in an industry. I mean, we're fortunate. We're seeing states, federal governments putting money towards the research and to the workforce education. We're seeing universities then applying that, trying to do the material science to try to bring down all three areas of the SWAP plus SWAP C, as you said. And it's all about jobs, and it's all about jobs in the free and open market societies of the world. This is a race, and we're all part of it, whether we realize it or not.
Yeah, and once again, going back to that really good pie chart that you put up earlier, there's just so many different modalities, right? And when we're referring to the challenges to scaling each of these modalities, they're very different and they're also very specific to that modality. So in photonics in particular, one thing that we benefit from is the fact that photons are essential. If anything, we get too many photons, right? And we only need one, right? And so that's the nice part about photonics, but then what we need to overcome is we need to be able to entangle those photons and be able to operate on those photons without losing them in transit, because it's a measurement-based architecture. And so for us, the manufacturing challenge, to answer your question, is about how do we build very low-loss integrated photonic chips, where we're able to then receive these entangled resource states, manipulate them, and then measure them at the end. And that's something that we're developing at ORCA. But to what you said earlier, if we went and looked at the offerings from different MPWs and different foundries, they're not quite at the level that we need. And I think that you'll find that across all of the challenges that we're all solving, across all the modalities of quantum, which is that what we need for quantum is so exquisite, and we require such a high degree of precision that if we need it, we have to make it ourselves. So that's part of the fun of the industry, but certainly part of the challenge in going from these ENIAC machines to our iPhones. Yeah. I think of as many.
Only use it once a year.
All right, so how about the networking space specifically, and the stuff that I'm seeing? I participated in Optica's event earlier this week, where they were talking about quantum key distribution, and I was really impressed that they had already rolled out several of the things, and they were talking about using satellites to distribute these keys which are used for encryption, and so that they can go over much larger distances than through a fiber. And let's speak to the modalities, and I think there's just one modality, right?
Well, that's a really good point. In the case of the networking, there are already initial testbed networks up and running that are quantum networks. So I can think of several of them. Illinois is a particularly well-funded state, as Greg was mentioning, that kind of has been pushing that technology. In New York, there's a company called Qnect, which has built GothamNet, where they have a quantum network through Manhattan and the greater metropolitan area. And so they've been rolling out other, I've forgotten, there's a city outside of Oak Ridge National Laboratory. They took that technology and they have a quantum network.
Oak Ridge?
Yeah, out of Oak Ridge, yeah. So look, but yeah, so entangled photons, networking is all about entangling the photons, right? We were talking about the two newer aspects of quantum that are kind of and this is about entangling photons, sending them away, far away from each other, measuring one and knowing what the other one is. And so you're right. And so how do you generate entangled photons? Maybe there's different ways to do it, but it's not as wide of a diversity of modalities as like computing is at this point. It's a much narrower set.
I mentioned earlier that photonics is really awesome. In all seriousness, I think quantum key distribution is becoming very mature, as you mentioned. A really exciting area of networking in my mind is how do you network between different quantum computing modalities through the same network. So that's an area that DARPA is highly interested in at the moment. There's an open solicitation on different proposals for optical interconnects between the various modalities. And that's certainly a really exciting area of how do you take an atom-based quantum computer and take that with photons and send it to an ion-based quantum computer and then have the two operate jointly.
That's a really good point, yeah. I mean, so there's a buzzword for that. It's called transduction, which is how do you get one kind of device to talk to another kind of device. If this has one wavelength and that has another wavelength, and then they just, on their own don't talk to each other, so you have to figure out how to convert, one kind of signal, one kind of optical signal to another kind of optical signal. And so that's actually a big problem with networking these days, and then a lot of people are coming up with different ideas, but you're right, that's kind of a big push, and like, how do you talk to, you're networking something on either end, and if they're different things, you need a way to like match the impedance, right?
Yeah, like two big programs that are kind of setting the standards for what modality means for quantum communication is one out of the New York area is Skynet with a Q, in collaboration with Qnext, but also Brookhaven National Labs. And there, I call it a heterogeneous architecture for quantum communication that does require transduction. Because it's hard to create quantum memories with photons. They tend to move really quickly and escape where you want to hold the quantum memory. So quantum memory might be a system created with superconducting technology, but then you want to move the entangled photons through optics, so you need transduction. Skynet is this heterogeneous type of architecture. And another example, counterexample, is called ASPENnet, another acronym. Well, less nefarious sounding, but that's, I believe, out of the Colorado area, and that is homogeneous. Everything's photonic, including the memories. And I think those are two really interesting big U.S. projects to watch over the coming years.
I agree with what they've been sharing. I don't have anything to add to it, except that I think a lot of the work that's being done in the research facilities at universities in particular, you're going to see more and more startups coming out that are filling a gap in a particular component of networking, and I think that's only going to make it more mainstream and more commercial. I would put networking as a close second in terms of commercial application to sensing right now in the near term.
So earlier this week, I heard something that made me kind of snort my coffee. Entanglement as a service. They're talking about,
Put it on the shelf.
they're talking about utility that like sells you entanglement, you know? And it's like, who comes up with this stuff?
An investor came up with that. We're not yet ready for prime time for that. I would submit to the audience.
That's a service.
Maybe. So let's pivot.
Let's pivot and talk a little bit about the second question. We got to wrap it up pretty soon. Quantum error correction has been demonstrated to work, so it is ready for prime time in commercial applications. Is it ready for prime time, or is it still, you know, work to be done to make that practical? And where do you see the challenges, and where do you see it being applied in the markets?
I'd like to jump into that. It's not done, but it's made great gains in the last couple of years. And I think that NVIDIA in particular has been pushing with their CUDA-Q platform. I do believe that we'll start hearing more and more about quantum error correction being applied into much larger architectural frameworks where there's a CPU environment, a GPU environment, and a QPU environment, where the quantum component of that architecture might provide a 0.5%, a few basis points of improvement in speed and energy and accuracy. But in these large data centers, that's tens of millions of dollars in terms of savings and productivity. But I think that'll be the first application. Small, incremental impact to start, like single function point stuff. But by getting in those industrial environments, the pressure on QEC to become much better, much more accurate, will be, I think we'll see it in the actual performance and the functionality that'll come out in the years to come. But I think it'll be accelerated. What took us 2 years to get to this point, great gains, I think will start being measured in 6 and 3 month increments in terms of innovation because of the pressure from that.
So this is interesting, but I can't really say that I can understand. I mean, I understand what I've read about quantum error correction. How is it being applied in this way that you're saying in hybrid computing?
Well, it's
environments?
irrelevant to have a quantum system, quantum computer system, involved in a broader architectural layout, say in a data center, without having some level of quantum error correction part of that architecture. It's sort of like the invitation that now it's become good enough. Not right where we want it, but good enough. There's now an invitation for quantum computing systems to start being part of much larger architecture.
Thanks for
Yeah,
that.
so I completely agree with you. That's our philosophy behind the PT series products that we deliver as well. And so what I didn't say earlier about our PT series is that it is a rack-mounted quantum computer, but it's also a hybrid system. So we do use a GPU cluster in conjunction with the QPU, essentially, like the quantum processor. And to piggyback off of what you're saying, what we do is we develop a neural network, so it's a hybrid GAN model, a neural network that uses both the QPU and the GPU cluster, but they're trained together. And so to a certain extent, right, the neural network that's implemented on the classical architecture provides the quantum error correction to the extent that's needed at this level for our QPU.
Interesting.
Yeah, I would just say, like, you know, in terms of the timeline of where we are with quantum error correction, it was only a couple of years ago that Google demonstrated scalable quantum error correction, and you know, they were limited by how many qubits they could get to work together to start a empirical graph. You know, so I think it's still really early stage, very early days, as you were alluding to, Craig. What is what's the classical hardware side? Where's the boundary between the HPC hardware and the dedicated to quantum error correction hardware from companies like Riverlane? You know, I think we're very still in the early stages for quantum error correction.
Yeah, the way that I would express this is that the research done by Google, the research done by Riverlane, and everyone else gives us the permission to scale, right? As in, with every additional physical qubit that we add to the system, we don't degrade the system more and more. So it gives us the permission to scale, but doesn't yet give us the ability to scale. And so we're still working on that second half.
All right, we're running out of time, so I'm gonna just ask for a super quick, like one-liner. Will quantum error correction be used in networking or sensing applications?
I think so. Engineering, but I don't think so in sensing. It's almost the inverse. They're so sensitive you don't need it. But you guys will say, you will find. My one-liners, I don't think so.
Well, there's different sorts of error correction problems for the communication example, where they have to correct for polarization as it degrades through the fibers. It's not exactly what I think of as quantum error correction.
Fair enough.
So it has its own natural problems. I would imagine that the sensors, they are qubits. And so you want to have a bunch of physical qubits working together to get a fault-tolerant qubit. So I think quantum error correction must apply based on that principle to sensing. Yeah, so I think like it is applicable for sensing. My physicist hat tells me it must be.
Tells me it ends up as a binary output though, instead of an analog output, because it's going to snap to kind of like an IC. I don't know. All right, let's open it up to the audience, maybe. Can I borrow somebody's mic? Jeff. Is it on?
Yeah, it's working. Well, I'll talk loud. So I'm not a physicist, but it caught my attention of Psi Quantum and their billion-dollar raise, where they're talking about a million qubits, and obviously there's a lot that's not realistic for that. My question is, from someone that's outside the industry, which I am, how much do you think that is realistic? A, and B, what do you think that people don't understand that read the headlines and maybe don't understand the physics and science behind it?
The science behind their approach,
Or just the quantum computing.
or behind the race of water.
Yeah, behind the actual like quantum computing. I mean, you mentioned early days in order to achieve there, but people see the headlines and there's a lot of stuff. What do you think people don't understand when they're writing the headlines for VCs and investors?
Yeah, I think one thing is, what I said about the permission to scale versus the ability to scale. Psi Quantum's approach is to take something where they have the slightest ability to scale and replicate that all the way to the point where they can get millions of qubits. And that's why their architecture, which is a linear optimal architecture, requires such a massive investment. That amount of money they raise is close to the amount of money that it costs to build one of those quantum computers. And also, to what Paul said earlier, it takes up a very massive amount of area, because in order to implement that architecture, which is a bit of a simplistic architecture, it takes tens of thousands or hundreds of thousands of CPU, of the data center racks to implement. We're just to plug ORCA a little bit, we were taking a little bit of a different approach. So we have a nonlinear architecture that greatly reduces the scaling complexity.
I would also say, for people who are like actually considering investing in things, if you're a part of this is creating job opportunities for physicists and VC firms, but also you can look for other indicators, groups that you can trust that they're doing the validation. And one that stood up in a big way, sort of a global way, is DARPA. They have a program called the Quantum Benchmarking Initiative, where their team of scientists are really getting embedding into different companies and scientifically evaluating their roadmaps for technical feasibility. And for them, what they're looking for is a utility scale quantum computer, in other words, useful, and for like scientific computations. And they publish who is being evaluated at different stages. They have a 3-stage process right now, and they're about ready to transition from stage 1 to stage 2. In stage 1, the attrition rate was about 50%. Of all the companies that applied to be part of it, DARPA said, no, this is BS right off the bat, cut 50% of it. Allison Bob is on that list, currently in phase 1. In phase 2, ORCA will probably be announcing that transition around November.
Marcia?
To add one thing, that you also asked a question about, for those that aren't familiar with it, those that aren't the scientists or trying to understand the quantum computing field, the quantum technology, because I'm not a scientist or an engineer, and the way it was described to me that I could get my head around, how many of you are familiar with the Enigma machine from World War II? It was cracked with a mechanical computer. But in the 40s and 50s, we started making investments into digital computing, zeros and ones, and that was the long bore commitment. That was it. That is what we use today. Quantum technology is fundamentally a different system. So that means we need to educate and train the workforce. That means we need to innovate differently. That means the applications and the use cases that we can apply it, how we're going to do it, and how we actually have to build that industry is just fundamentally in its infancy, and it's different. The last thing is, in quantum tech, it's not just about physicists and PhDs and engineers. I think like 45% of the jobs are for certified electricians and certified welders. It's a different industry altogether.
Yeah, I'd like to just pile in on there and say, yes, it's a whole new industry. That's absolutely right. And so that means growing it out from top to bottom, a lot of new technologies. I mean, for those of you in the crowd who are students, I envy you. You have a lot of opportunities if you want to pursue.
Yes.
Because this field is going to evolve and grow for decades. I personally. But yeah, you're absolutely right. I mean, when was the first binary digital computer made? A long time ago, and look where we are now that we carry them around in our pockets. Quantum computers are intrinsically different kinds of machines. And so this is going to be in a very evolving field for quite some time.
All right, everyone, I think we've run out of time, and we have the panel here afterwards, so if you did not get your question asked, we are continuing the networking. And so you can just walk right up and ask questions during the networking session. Everyone, thank you to APS. Thank you to the panel who traveled here in order to be here in Austin. Thank you to you guys for making this a successful event.